Okay, so today we're going to talk about classification, and I'm going to conclude quickly this topic, classification topic. So you remember almost last 2-3 weeks we have talked about predictions. That was we started from I guess 2-3 weeks ago. Then we talk about regression, linear regression, a little bit non-linear regression. So those things can be seen as a classification problem. So, for example, the examples that we saw about predicting the average salary of public workers in San Francisco, the baby height based on their parents' height, or baby weight based on gestational days, those are basically could be seen as a classification problem. So classification are the things that you're going to see always in machine learning. So we're going to work a little bit about that. So another things I put note here that I mentioned is the regression that we used was mainly for numerical data, but classifications are mainly for categorical data. We're going to see that. So there are a lot of examples can be mentioned for classification example. For example, it can be a classification algorithm looking at the like MRI pictures from the head, from the brain. Then you can detect based on the MRI pictures if brain has any cancerous cell or not. Okay, just by looking at this. So that can be one type of application for classifications, and it's very popular application actually. We've seen this in a lot of diseases, a lot of chronic diseases, brain tumor, I don't know, heart problem, kidney problem, a lot of things can be used for classification can be used on that. Another one can be, for example, classifying some emails as spam or not spam. I don't know how much you have seen the changes in your lifetime, like online lifetime, on email improvement, but those back days, the emails they were full of the spam. But now you see, for example, Gmail claiming that if I'm not mistaken, they are eliminating 99.9% of the spam successfully. So our emails are way more spam-free these days. So that can be basically another classification example. For example, looking at the emails and deciding if this email is a spam or not. Basically classifying, is it goes to a spam class or goes to the normal valid email class. By looking at the pattern, for example, of the subjects, senders, receivers, a lot of basically parameters can play role. Another one can be like autonomous vehicles, the thing that is getting trend. For example, in this example, you have this image processing algorithm that is looking at objects in the road and deciding, for example, those objects are safe to pass over or not. For example, the car camera is seeing these two cars, and they know these are cars. This object that camera sees is car, so you cannot hit them, you cannot get close to them. But for example, this I don't know, white lines in the surface, they can be safe to pass over if, for example, they are not continuous line, you can basically pass over. That can be another classification example. If another classification example, for example, was the case that let's say, for example, for online banking, those you most probably have experienced this sometimes in your life that when you do some certain transactions, you may receive a call from your bank that is it you really doing this transaction, or you might receive a message, you might receive a notice in your application to double, basically the bank is double checking with you that is it you really taking this, doing this transaction or not. That's another type of classification that the bank wants to know if it's valid or not. And the bank basically detect this suspicious transaction based on some parameters in your transaction. For example, you're doing all the transaction in Mexico in like 5 hours later, if after your last transaction in Mexico, you have one transaction in London, but that's a little bit suspicious because not little bit, that's definitely suspicious because I mean, looking at those parameters, you can decide. Another one can be the case that happened with Cambridge Analytica in the US election and also in the Brexit elections, that they had basically, they were classifying the voters, and then they had a targeted advertisement based on what class of voters you are, or basically based on what pages you like on Facebook, what you comment, which people you're following. So they were classifying the voters and then sending them, how to say, targeted advertisement, targeted news in order to basically influence their decisions on the elections. So those are some examples of classification. You can see a lot of, most of maybe machine learning algorithms are involved with classification. It's the same thing that we use in our daily life too. It's not just in computer. For example, as a dummy example, maybe when you go buy a fruit from a shop, I don't know, you go to buy avocado, then you take avocado, you look at the skin, you press it a little bit to see how hard it is, how soft it is. Basically, by considering those parameters, you're classifying the avocado that you're trying to buy. That is it a good one or it's a bad one. So that those can be seen as a classification problem. So let's talk about it on code a little bit. So if you, I don't know if you're going through my codes, sometimes I use some new, basically, some new packages that you just make sure if you're using that, just uncomment that to install that, because later I'm gonna use this plotting. So the table we're going to see today is this chronic kidney disease. So basically what it shows, that it shows blood tests for a lot of people, around maybe 150 people, that with their age, blood pressure, and some certain basically result in their blood test. For example, how much they have sugar, their red blood cells, glucose, bacteria, sodium, potassium. So we're going to see in all this basically things that we can find in a blood test and decide whether the person has a chronic kidney disease or not. But the class in the last column, the class is defining if it's one, it's if the person has chronic kidney disease. If it is 0, the person doesn't have chronic kidney disease. So these are basically our sample from 150 people. So if I class them by the groups, as you can see, we have 115 people without chronic kidney disease and 43 people with chronic kidney disease. So we're going to see how we can basically apply the classification example in this particular case. So if I scatter plot, for example, the number of white blood cells, okay, and the glucose in the blood, and then they color them by the class. For example, the yellow ones are those people that have chronic kidney disease, and the blue one, dark blue one, is the people without chronic kidney disease. So what can you tell me looking at this scatter plot? Can you classify, basically, the question is, can you classify the person based on glucose and white blood cell that tell what, if, for example, white blood cell is below certain number, glucose is below certain number, then you most probably you don't have the how to say, kidney disease. But if you're above certain threshold, then you have. What do you think? Anyone can share his or her idea? I'm waiting At least 1-2% tell me something about this. So what we are doing here, we are looking at these two parameters, white blood cell counts and glucose, and we are trying to see, can we classify them based on this? So what do you think?
We may be able to, but we can still see some class 1 points overlapped with the class 0 points. So it might not be as reliable as we might think.
Okay, yeah, true. It's you're saying, okay, if for example, if I say if the glucose is below 170, 150, and white blood cell count is below 1,200, then most probably I cannot say. But if it's below, for example, this line, this line, for example, from here, if your glucose and blood count, white blood cell count is falling in this area, then most probably you can say you are having the chronic kidney disease. But if it's below then you cannot say by sure, because you see a lot of overlap there. That's right. So that's why let's look at another parameters in that blood test. So this time we're going to look at the hemoglobin and glucose and see what we will see. What about now?
I think that for this case will be a better representation of the clusters. I mean, you can have a better result having the hemoglobin and the glucose.
Okay, yeah, in chat also, Diego is telling yes, much better. Yes, as you can see here, for example, here now we have a better classifications. For example, I say if your hemoglobin is I don't know, about 13, and then your glucose level is below 100, I don't know, 70, 60, then most probably you're not having the chronic kidney disease. But if it's above these levels, you're most probably having the kidney disease based on the data that I have, right? So this is one, for example, classification example that we are looking at these particular parameters, and we are deciding to see if there is a class, if we can, for example, differentiate. For example, if now I get a blood test from a new person that is not included in my table, this table, the people. So looking at those parameters in a new person, I can say, and then I do this, I plot that for the new person, new test that I get, and I see, for example, the person falls in this point, then I can say, okay, now based on this, you may have chronic kidney disease based on this data. So let's look at another examples. This is, we are still using banknotes, the notes, money. So this table shows basically we have there are some counterfeited monies in the outside is circulating. So those are basically not real, not basically printed by your central bank. They are counterfeit money. But this table shows two classes of these monies. One is class 0 is basically real money. Class 1, we cannot see here, is the counterfeited money. And what they did is, this is like image processing study research. So they take pictures of the notes and of the money, and then they had basically these parameters of the pictures: wavelet variance, wavelet skew, and wavelet chord entropy. I'm not going to talk about this. It's basically little out of my topic even, what these things especially means in a picture. But they studied these parameters by analyzing just the picture of the banknotes, and then they put these basic parameters, and then they classify them as a 0 and 1. So basically, this classes comes from the actual observation. I know this certain nodes is concentrated, I take picture, I know this is real, I take picture, and I study all of them. So if I do the same thing, I do the scatter plot based on the wavelength variance and wavelength curve, and group them by color, then we'll see this. So looking at this again, same as what we did before, there are a lot of overlapping dots. So you may say it's not a good classification. It's not a good parameters to look for classification, or basically differentiating if the banknote is real or is counterfeited. But again, you'll see this clear line from here. If basically they are above this this line, you can say for sure they are counterfeited. If they're below this line, you can not say by sure. Okay, there are certain pattern, but not very clear one. So if we look at another two parameters, is for example wavelength skew and entropy of the pictures. Again, you see something like this. There are a lot of overlapping points. But looking at this, you'll see some patterns. For example, I don't know, you might look at this scatter plot and say, okay, if I look at these two parameters and if they follow this, for example, this line, I'm going to say they are counterfeited. If they follow another pattern, I'm going to say they are not counterfeited. You may do that. So, but you may do another things. So what I'm doing here, I'm just looking in this, for example, the first one, I'm comparing these two, wavelength and these two. Another one, I'm looking at wavelength skew and entropy. I'm looking at these two. But what I want to do now, I want to look at three of them: wavelength skew, variance, and this curve. And I see if I histogram all three at the same time, what I'm going to see. And you can do that basically, you can do that with the table in the data science package. But what I decided to do it using the basically Panda and Plotly Express, which is make it much easier, much shorter the codes, much easier to understand. So what I'm doing here, I'm putting the wavelength skew in X, variance in Y, and curve in Z, and I'm drawing 3D scatter, and I'm classing them from 0 to 1. It's just two class because we have just two class, so it's showing like as a heat chart here. So if I make them like this, then now I can look at it in a better way. Can you see the figure smoothly when I rotate it?
Yes.
Okay. So this is what I see if I draw a 3D scatter plot. So as I'm rotating it, you can see there is a clear distinction between all these points, right? There is an absolute clear difference between all these points. If you look at this, for example, this way, you can see they are clearly separated from each other. Sorry, I don't know what's happening. Okay, so what I'm doing here, I'm looking at all three at the same time now. Okay, previously we were just looking at two parameters. Okay, these two or these two, but now I'm looking at three, so I can have a better distinction between the parameters. And as I'm rotating this, you can see there is a clear distinction between them, right? So based on all those three, I can have a good classification. If I look at it like in 3D plot, I can have a clear distinction between them. So just keep this in mind. You remember the last one, chronicle kidney disease that we see. We also draw just based on two variables, two parameters. Here, hemoglobin and glucose. Here, for example, glucose and white blood cell count. But it's not possible, for example, I look at all of them at the same time because we are living in a 3D world, so we cannot easily imagine a 4D or more than that. I cannot even like how to say, visualize it. So we're going to see how we can do, what method we can use to see this type of distinction between the variables. Is there any questions so far? Is it clear what we're talking about? Okay, I see some shaking.
I believe so.
Okay. The good thing with turning on your camera is I can look at your face and I can see if you're puzzled, if you're comfortable, it's basically, I can see you're getting it or not. So, but when I don't see, it's like, okay. Anyway, I see some people shaking head, so they're okay. So let me go to my slides. So that's what the topic of today. Basically, we're going to talk about classification, classifiers. So as you see, we have certain attribute of examples, examples. For example, in the chronic kidney disease, white blood cells, I don't know, glucose. We're going to look at those and we're going to use them in our classifiers, and then we're going to end up having predicted label of the examples. So we have the population. You remember again those terminology. We have a population. It's not possible really to have to study all the population, right? It's not possible for me to look at all the banknote in the world and like decide if they are real or if they are counterfeited. Or I cannot test all the people in the world and say, see if they have chronic kidney disease or not. So what we have is just a small sample. We have just access to that. This is what we discussed almost from very beginning of this course. So we have a small samples from our populations. So what we have was only the samples to study. So now what we have there, for example, in the chronic kidney disease in the banknote table, we had the sample and we already labeled them. So we have the sample, then I label them manually, okay? By looking at them, by studying them, I label them manually, for example, counterfeited banknote, non-counterfeit or real banknote, or people with chronic kidney disease, or those without chronic kidney disease. So we have samples that are labeled. So these samples and label, what we're going to do in our classifiers, we're going to divide them to two groups, training set and test set. Basically, one part of that samples I'm going to use to train my classifiers. And then with another part of those samples that I have, which is totally separated from the training set, I'm going to keep those. I'm not going to let my classifier touch them. I'm going to just keep them for testing later my classifiers to see how well my classifier do on the test set. So basically what I'm going to do, train them with the training set, then I'm going to test them with the test set. So this is basically model the association between attributes and labels. Then we use test sets to estimate the accuracy of the classifiers. Sometimes you may see some people, you may see some other division like the validation test too, validation set. That is, I'm not going to talk about that much, but the validation set is basically something different from training set, from test set. It's used for adjusting basically your training set, your parameters, or making sure that you are not overtraining your model. So I'm going to talk about that with these examples. In a Google Science Fair, I'm pretty sure, maybe you have heard about it. It's basic science fair. People, students from all over the world, they participate with their project. So in this particular project in 2012, Brittany Wenger was 70 years old, high school students, won by building breast cancer classifiers with 99% accuracy. So he got basically won that science fair. He got to see the sitting president by that time. So what he did, he was looking basically at the pictures, okay, at the pictures and trying to see if there are benign or malignant, or basically if they are normal or cancerous cells for the breast cancer case. What we're going to do today is we're going to follow her steps and see what she did, and if we can replicate her experiment and achieve the same accuracy of 99%, which is pretty high and pretty impressive. So let's see what we did. So the good thing is the data is publicly available. This is the data. So this is the breast cancer table. And I put it in the patient table. So what I'm having here is all these things that I don't even understand very well. The parameters, okay. Clump thickness, uniformity of cell size, of cell shape, and then considering all this, then we have the class, okay. So if it's 0, the cells are not cancerous. If they are 1, they are cancerous. So what we have here, we have 444 non-cancerous examples and 239 cancerous examples, okay, in this table. So again, this is our samples, right? This is the whole sample, the one that we're going to use basically in our classifiers. So what I can do with this is I'm going to first do the histogram of all these parameters. And I want to see what I can find out from this histogram. So I put the patient histogram overlay false. If you do this, you saw in other examples, you can get all this basically histogram of all these columns. Sorry. So this is what I get. So from clump thickness, uniformity of cell size, cell shape, marginal attention, single epithelial, bare nuclei. I cannot even pronounce them. And we have this class, of course, the class 0 and class 1, basically non-cancerous and cancerous examples. So what can you tell me just looking at these histograms? Can I use this for classification? It's totally useless, or what do you think?
What was the question?
I mean, I did this. You know, we get to see this a lot of time in this class. We get the table. The first thing we do the scatter plot, we do the histogram, and that was what we were. I was trying to highlight. Like first visualize, then quantify. Of course, you have to quantify, but visualizing is going to help you. So I come up with this idea. Okay, I want to visualize, so I'm going to use histogram for all these columns. And my question is it valid work? Am I getting any knowledge out of it? Does it helping me?
Maybe no, I don't think so, because you have each value in our
Yeah, it's not going to help much because what I can see, I mean, what I see here, for now, let's say it doesn't help much. I believe it does help a little bit because what you see is, for example, in clump thickness, there is a lot of variation for all the samples. In uniformity of cell size, there is a big jump in this part for this value. For this one, cell shape, you see the same pattern. So big jump in this value. For marginal attention, a big jump here. For this, a big jump here. For some of them, it's like some values are very important. For example, for this one, here you see a jump here, but not much here. So you might later want to look at these particular values, okay, and see what you can do with them. For example, maybe this doesn't going to help you much, okay? Just I'm giving you a very abstract idea. But anyway, just looking at this, I cannot conclude anything. So what I want to do now, I'm going to use scatter plot, considering these two parameters, plant chromatin and single epithelial cell size. So what I see is, let me minimize this. What I see is this scatter plot. So I have all this yellow one here +1 for like cancerous cells, and so the blue ones here. But you see some of them are like dark yellow. Those are basically overlapping points. So basically what it's telling me here, there's a blue, there's a yellow, and they are overlapping each other. So just looking at it, again, you see you cannot really differentiate or draw a certain line there and see if you're above that, you are not cancerous, or you are cancerous. If you're below that, you are not cancerous. That's what, because we have a lot of overlapping dots there, and I don't like that. I want to see more basically are separated from each other. So what I'm going to do using this functions, I'm going to add a little bit noise on that, a little bit jitter on the points to draw them in different points. So what I did, basically, I add to all those values a little bit jitter, a little bit noise, so I can draw them in different parts, so they don't overlap, or they overlap, but I see clearly how many points I have at each part of the scatter plot. So this is what we get here. So now there is slightly better, because we see, even though there are some overlapping points there, but they are not many, but there are a lot of, for example, blue, dark blue cells here, dark blue examples, or basically non-cancerous examples in this bottom corner, and most of the cancerous cells are falling in this part. So now looking at it, you might say, okay, now I can basically separate them a little bit more clearly, but still not completely, because there are a lot of overlapping. If you draw your line here and say above this line cancerous, below this line non-cancerous, you're not going to get a good estimate of that. Any questions so far? So let's keep this here and see. We're going to talk about the distance. So let me see. So this slide just is a reminder for you to what you can do with the tables. Each row contains all the data for one individuals. Using t.row I, you can evaluate height row of the table T. Using this, we can get this at particular item. So if all values are numbers, then np.array, this evaluates to an array of all the numbers in the row. The benefits here is if you convert them to array, then you can do, for example, multiplication of two arrays, diffraction, addition of two arrays. So that's why this is going to be helpful. If you convert the row in the table to array, it allows you to, for example, do diffraction, adding them, and do a lot of things. So this was a question Umberto was asking me last time, that it was not working, but it's working. So to consider each row individually, you can use these codes for row in t.row, some codes here. So basically what this loop's going to do is going to go through all the row and do some whatever you want to do with that. So this is just for you to remember those things. So let's talk about the distance between 2 points. Basically, you see in our scatter plot, okay, we have a lot of points here. So I'm going to see how the distance between 2 points is going to be useful for me. Because, for example, if I say all the non-cancerous cells are here, okay, in this point here, then for example, I do another test, I get the point here, and I want to decide that if this point should be categorized as non-cancerous or cancerous. So then I might be interested in to calculate the distance between my point with all these points and decide based on that distance. For example, if it's here, the distance between my examples with the non-cancerous are very big, and it's more closer to the cancerous cells. So I'm going to classify that particular example as cancerous. So the distance is important. So we're going to see the distance So you know two attribute you have when you have two attributes x and y, you can calculate the distance between 2 points using this. This is the Euclidean distance formula, nothing weird. If you have 3 points, you can use this. Okay, this is nothing new. It's just calculating Euclidean distance between 2 points. So this is 2 points. This is for 2, this is for 3, and you can consider that for more than 2 points. So let's do that now. So I defined these two functions. Okay, the first one, distance, calculate the distance between 2 points, represented in an array, and then raw distance, calculate, I get 2 raw from my tables and calculate the distance between these 2 raw. Is it clear? So this is the table that I have. Okay, I'm showing just 3 rows. I dropped the class because I don't want to consider that class now in my calculations. Okay, I put these patients for basically, this is the one for breast cancer example. I dropped the class column and I put this in the attribute table. So now I can use this to calculate the distance. For example, here is the distance between row 0 and row 1. Basically what it means, this distance, this number, is I'm getting the distance between all these points, okay? All these points that you can see here in the row 0 and row 1, I calculate the distance, considering all the parameters. So I get these numbers. So if I calculate the distance between a row with itself, it's going to be 0 because there is no distance between 2 points to exact row. So for example, if I calculate the distance between row 0 and row 2, it's 2. So just looking at this, what can you say? For example, you see the distance between row 1 and row 0 and row 1 is this, and between row 0 and row 2 is this. So you can see it varies, right? It varies between different rows. So basically, it depends on this parameter that you see, all the parameters. So this is a way for me to do this, okay? Here I have only three parameters. I can look at it. I can draw the 3D histogram and I can see clear distinction between this yellow and blue one. Basically, yellow was the non-cancerous. The blue is non-cancerous. Yellow was the cancerous. I'm just play around with it. I can see there is a clear distinction between them. But here I have more than 2. I have a lot of parameters. I have how many? 2, 4. I have 9 parameters. Okay, I cannot draw a 9D scatter plot and look at it to find that clear distinction between them. So what I can do is just calculate the distance between all these rows. So I see for some row, my distance is bigger. For some row, my distance is shorter. Is there any questions so far? Is it clear what we are trying to do? I mean, I hope so. Okay. So now we're going to see how this distance can be helpful for our classifiers. Okay. So as I mentioned in that scatter plot, I want to, for example, to calculate if this particular point is close to my non-cancerous cell or cancerous examples. So for that reason, I'm going to calculate the nearest neighbors. Most probably you have heard about it. If you don't know already, I'm going to consider the k nearest neighbors. I'm going to use these algorithms. To find the k nearest neighbors of an example, I find the distance between the examples and each example in the training set. So I have, for example, I want to calculate the k nearest neighbors from my, I don't know, row 2. Then what I can do, I find the distance between the row 2 and all the other rows in my training set. Then I augment the training data table with a column containing all the distance. So after I calculated all the distance, I'm going to append this to my table that I already have. Then I'm going to sort that table, okay, based on increasing, by increasing order of the distance. So basically, I want to see if I'm considering the raw 2, which other raw is the closest in the distance to my basically studied raw, which let's say is 2. Then I'm going to take the top k row of the sorted table. So this is basically a very plain English explanation of k nearest neighbor algorithms. I'm going to calculate the distance, and I'm going to see, for example, if I'm calculating 3 nearest neighbors, if my k is 3, then I'm going to order the table based on the distance, and I can get the least 3 rows with the value of the distance. So let's look at it in the code. So I define this function distance, which compute the distance from example for each row in training. So it's get my row, and then it calculates the distance between this with any other basically row. You can see it, I'm using this row in attribute row basically to go through all the row in my table. Then I use this basically function raw distance to calculate the distance, and I'm appending that to this array here. Then I return the training, the table with that with this distance appended to it. Then the other functions is returns the closest function returns the table of the k closest neighbors to example. So in this one, it gets the training, it gets my example, and it gets k. For example, it's 2, 5. It's like 1, 3, 5, 7, whatever, and it calculates. It tells me the k nearest neighbors. If it's 3, so the 3 nearest one. So what I want to do, I want to look at the patient in my patient table. I want to look at the raw 12. So I'm going to look at this one. So you can see I have this raw. So this raw is classified as 1, which was cancerous. So I'm going to calculate the distance between all the other rows with this particular raw, and then I'm going to order my table, and I'm going to see how it shows. So this is this raw. I put that in examples. Okay, this is the same raw 12. So now I'm going to calculate this distance between my raw 12 with other tables, and I'm showing the 5 nearest one. Okay, the k is 5 here. So basically, what I'm doing here, I'm calculating 5 nearest neighbors. So I calculate the distance of all this. Where is the table? All these ones. Okay, I calculate all this distance between all these rows, all this 673. I append the distance to the table. Then I put the distance and I order them in terms of the distance. So this is the 5 closest row to my row 12. You remember, I ordered them, okay? I ordered them by the distance in an increasing fashion. So any questions so far, what I did? Is it clear what I'm doing? Some reactions?
Why did you choose row 12?
Pardon?
Why did you choose row 12?
It can be anything. I'm going to show you other examples too. It's just one example.
Okay.
It can be 10, it can be, it doesn't matter really. I can do it with another one later. So I have this, yes, question?
It's similar to what we did in Lab 9, no? The one for the movie classifications?
Exactly, that's what I was asking you to wait, because I thought it would be much clearer for you have to do that basically project after to do this, because that's what exactly you're doing in the project tree for classification of the movies. Is it a romantic movie? It's action movies. You are doing exactly the same things.
Wasn't that Lab 9?
Lab 9, I'm not sure, but this is exactly the project. The project is about classification. The project tree is classifying the movies.
I believe it was the checkpoint, everything until the checkpoint for the project.
Yes, true.
Okay.
Mhm. So, okay, I get this table. I'm going to define another two functions. Majority class, basically what it does, it returns the class with the highest count. So it look at these classes and return these classes with the highest count. So what I'm doing here now is, if you look at this table, so these are the 5 closest row to my row 12. Okay. So if you look at the class here, you see the first one, the closest one, the class is 1, cancerous, right? The second one is 0, non-cancerous, non-cancerous, cancerous, non-cancerous. Okay. If I look at this, then, and I'm looking at the 5 nearest neighbors, then I want to now classify my raw 12 based on this observation. I'm going to classify that as a non-cancerous. So basically, the classify function returns the majority class among the k nearest neighbors. Basically, it's return the majority of these classes. So you can see the majority is 0. You have 2, 1, 2 non-cancerous, 2 cancerous, 3 non-cancerous. So this function is going to return this. So if I look at my raw 12 with this training that I did, 5 closest neighbors, 5 nearest neighbors, I'm going to classify my raw 12 as non-cancerous. So was it correct classification? So yeah, as Sean shook the head, it's like true, it's not. Because you remember the 12 was cancerous, right? 12 was cancerous, but I look at the 5 nearest neighbors and I find out this is not cancerous. I did mistake. So what if I calculate the 3 closest neighbors? I get 0 because if you can see again, the 3, 1, you have 1 here and 2 0, so the majority is 0. If I do the nearest neighbor or 1 nearest neighbor, or you call it like nearest neighbor, you get correct classification here. So you ask me why 12, let's go for any other one. You tell me the number.
80.
80. So let's look at the 80. So which one? Which K I should consider? Anyone?
10.
10? Okay, that's good. I wanted to get to this point. Because we are voting here, okay, to see what's the majority. So what you want to do is you want to go with the odd number. If you put the even number, if I put even number 2, I'm going to get 1 class 1 and 1 class 0. So it's going to be, the voting going to be equal. So I'm not going to calculate, I'm not going to be, no, is it 1 or 0? That's why for these k nearest neighbors, we usually consider the odd number. So 1, 3, 5, 7, 9, 11, or whatever. So I go with 3. Sorry, 3, that's not 3. So I calculated 3. If I look at the raw 80 here, you see the raw 80 is classified as 0. So if I put here now raw 80, those are just for you to see. Raw 80 here, 3 closest neighbors. I classified as 0.
Professor,
You need to exclude it also in the
yeah, that was
line 29, right?
That was what I
Oh,
was
so
gonna
sorry,
ask.
yeah, sorry. This is 80. Yep.
Yep.
This is 80. Classify. But so this is just for representing here. But what I'm putting here, that's exactly the thing. So no matter I put here 20, let's say 3, it's 0. Okay, it does everything. This is just for how to say, for showing you here, okay? So you can see 20, if I put 20 here, you see 20 is classified as 1, okay? Originally it's 1. If I put 20 here, you see, so what's happening here? So, 3 closest neighbor. I'm missing something here.
I think it's the,
Yeah.
yeah, that's all.
Yeah, true. I missed that. So if I calculate that, I calculate the closest one, the 3 nearest neighbors for raw 20, I get 1. Because you can see here, they're all categorized as 1. My raw 20 is 1. So this particular example, my classifiers classified my examples correctly. But you see in some case, it doesn't classify correctly. Like, I don't know, let's try 30. I should drop that. 30, let's say the same 3, or let's go 5, or let's go 7. So this is the closest one. You can see the patient 30 is non-cancerous. I calculated it's 7. It's all their, what I'm doing here, so rare. Yes, it's true. The distance is 0. It's pretty rare case. Closest patient exclude 30. Example. True. Yeah, that's true. I'm doing this correctly. So for 30, if I do this 7 closest neighbors, 7 nearest neighbor, I get 0. Okay. I think I broke it somewhere because they are all showing the same data. It shouldn't be the same. It's all same. So let me run everything and put my attribute. Let me see, I go back to 12 and see what I did wrong. If I get the correct one here, let's say 5, 12. Yeah, no, that was correct actually. But that was pretty weird because they were all exactly the same thing, but that was valid actually. Because I cannot see all the tables, I thought it's a weird things, but they were all exactly the same thing for that raw 30. So, but the idea is, I wanted to see if there is any confusion here. You get what I'm doing here. I said, for example, in this example for raw 12 or any other raw that you say, I excluded from the table. That's my example. Then I calculate the distance of all the other 600 with this particular raw in this example 12. I calculate the distance. I append the distance here. I order them in increasing form. So I have the closest one here. These are the 5 closest. So if I do the classifiers, so for my raw 12, let's say, I don't know, whatever, 5 closest neighbors, nearest neighbor, I'm going to get 0. So you see, this is absolutely wrong because originally it's 1. It's basically cancerous, but I classified non-cancerous. So your classifier is not going to return all the times the correct value, but you see in a lot of times it's going to return the correct value, and we are going to talk about it in the evaluation part. Any questions so far? So if no, let's have 10 minutes breaks, then we come back and we talk about evaluating this, evaluating my K, what K I should consider, and so on. 11:10, let's get back. Resume. So it was not basically a problem. You can see if I put increase, then you see this, this value is different for this last one. But because basically I assume these are the characteristics of the normal non-cancerous examples. So any questions about what happened here, what we did? What is K nearest neighbor? Okay, so let's go to my slide. So you see, so we talked about, in that example, particularly, we talked about nearest neighbor classifiers. We had this attribute of examples. We look at all those things. Then we basically train our set based on the attribute of examples that we had. So we consider all of them, all the things that we had. We consider all those attributes for training set. We train our model. Okay, basically that's, you can see that training is exactly what's happening in a lot of machine learning algorithms. We train and you validate using the test set. So we train them by the training set. Then we basically look at that particular raw and we compare. So we use the label of the most similar training examples in our classifiers, nearest neighbors classifiers. And using that training set, we try to predict the label of the examples. For example, in that example, 13, 12, the one that we saw earlier is like, based on the training set that I have, now I'm trying to predict this. And I see if my prediction is correct or not. So basically, to classify a point, we find its k nearest neighbors. The k can vary from 1, 3, 5, 7. And we remember we said you put an odd number here because it's like a voting, so you want to have majority for sure. Then we take a majority votes of the k nearest neighbors to see which of the two classes appears more often. Then we assign the point, the class that wins the majority of votes. So in that particular example 5, we saw, I said, let's say calculate the 5 nearest neighbors. I take the voting was 0, but that was a wrong one. But what does it mean? You see there are some correct predictions, some wrong predictions. So what we want to, basically what we want to do, we want to evaluate the whole classifier. We want to see how the classifiers does overall, not just one particular example. So for this reason, we're going to talk about evaluations and see what is the accuracy of our classifiers. The accuracy of classifiers on the label data set in the proportion of examples that are labeled correctly. Basically what it means, like I'm not going to look at just one particular example, I'm going to look at all the data and see how many of them I can predict correctly. Of course, some of them are going to be on correct predictions, some of them are going to be on correct predictions, that's like the example we saw. So I'm going to see how many of them are correct, how many of them are incorrect. So need to compare classifiers prediction to true labels to find out about that. Then if the label data set in a sample at random from the population, then we can infer accuracy of that populations. So now I'm going to do this. I'm going to have my sample separated into training set and test set and see the accuracy of my data. Basically, I'm going to train with this, then test it, and then calculate what is the accuracy of my classifiers. Any questions? No, let's go on.
Yeah, teacher, I have a question.
Yes, sure.
How do we choose the sizes of the training set and the test set?
It's pretty much up to you, okay? But usually, what happens in real life is more goes to the training set. I don't know, like 80%, 70% to the training set because you want to train your classifiers pretty well. Then you can do the like you may leave 20-30% for the test set. I can not tell you an exact number because there is not an exact number. It's pretty much depend on your model, on your sample, how big is it, okay? But usually what's happening, usually training set is bigger than test set. That's a usual case. But
okay, and for the K, how do we choose it? Like you mentioned that it must be an odd number, but does it have to be an odd number that is near the number of classes in your data, or it doesn't matter? It just needs to be an odd number.
Okay, these two are very good questions. Okay, let me, for example, put one another example here. 50. Okay, I'm going just to see what's happening. Okay, this is 50. Okay, in my example, I'm going to basically calculate the distance between the table with the raw 50. So what I'm seeing here is this. Okay, this is not a good example to talk about it because majority, even if I get 1, 3, 5, 7, everything, the prediction is going to be correct. I guess this is 50. Yes. So let's go to that 12. That's why it was 12, because it makes things more clear to talk about things. Okay. Let's have 12. This is okay. Yeah, this is the 12 one. So in the 12 I calculate. So here is exactly your question getting valid, because if I calculate one nearest neighbor, right, I'm going to predict it correctly, right? If I go 3, I'm going to predict it incorrectly, as you see. If I go 5, I'm going to predict it incorrectly. If I go 7, I predict it incorrectly, and 9 is still incorrect. Okay, so there is not really again, I guess choosing the K, it depends on your data. Okay, but you may want to do something. You can do something. Can you tell me what you can do? For example, you may want to say, okay, I want to make a loop. Okay, I'm going to go from one nearest neighbor, 3, 5, 7, like all the way to, I don't know, 11 nearest neighbors, and I'm going to calculate the best accuracy that I get. Okay, let me talk about the accuracy, then I come back to this choosing the K. Okay.
Okay. Okay. Thanks.
No problem. So what we were trying to do is we want to see how well the algorithm does overall. So we have this, the patient, the table, and we have 683. What I'm going to do here, I'm going to shuffle them, okay? You remember, I'm going to basically to shuffle them around, because if there is any ordering there, I want to eliminate the ordering. So that's why I'm shuffling them all the way around. So for shuffling them, I just take the sample without replacement or with replacement pause to move them around. Then what I'm going to do, I'm going to put half of them in training set, half of them in the test set. I mentioned training set, test set, usually there is a different variance, but in this particular example, I'm dividing it half and half. You can do pretty much anything you like, but usually it's better to have training set be here. So then I define this function to evaluate the accuracy. So what it's going to do is basically, it's going to, for example, going to do through all the rows, run the classifiers on the patient in the test set for all of them. Then it's going to see if this, for this particular row, with this particular K that I'm calling the function with, if my prediction is correct. If my prediction is correct, it's going to add this num correct. It's going to increase it one by one. Then at the end, I'm going to divide my number of correct predictions divided by all the number of rows to see the accuracy. So in this example, I'm calling this training set, test set with the K5. And let's see what we get. So basically what it does is goes through all the rows, okay? Take one row out of it, calculate this row and compare it with the 5 other closest, basically 5 closest neighbors from this table, okay, from my test table. And then it says like, okay, for example, in this particular case, 90. Oh, wow, that's pretty high. 98.5% of my prediction is accurate. Is it clear about what we're doing?
Yeah.
So for my training set, based on my training set, which was the half of the table. So I'm training with this training set. Now I have this training set, then I'm going to the test set and I'm calculating the 5 nearest neighbors. And I see what accuracy I can get. So basically I can predict the new model if I get another one out of this table. you bring me all this new test that you did from the person, you bring it to me by 98.5%, I can predict if the person has cancer cell, I mean, breast cancer cell or not. Is it clear? So what if we do this with one closest neighbor? Let's see what we get. Before I show you, you think the accuracy is going to increase, going to decrease? Any guess? There's no wrong answer. It's just a pretty much guess. Increase, decrease?
Increase.
One also says it's increase. Let's see. It's like 96.4%. So basically, it's quite a blind prediction, right? Because we cannot predict it. Okay, that's what I'm going to back to the question of the choosing the K. If I do it, let's put it in a whatever. Let's change it to 3 and see what we get with the 3 nearest neighbor. I want to see if I can go about this or not. This is pretty high. Even when I was putting this here, I never get this. So 3 gives me 97.9%. I can go up 7. Let me call it a few times. I don't know, 9, 11, 13, 15. So 7 gives me that, 9, 11, 13, 15. Let's see what they gives. So 9 is giving, 7 is giving exactly the same thing, same accuracy, as you can see. You see for 1, we went slightly lower. For 3, we were slightly lower. For 5, we get the highest. 7 is showing me the same accuracy. For 9, we are getting this accuracy. So it's good to put it here. That's like 1, 3. I want to use C2, all of them next to each other. So it's going to take a little bit of time because I'm calling all of this. So for the K, what you're going to see, as I mentioned, there is no really a right answer here. What the K number should be, you're going to calculate the 3 nearest neighbors, 5 nearest neighbors. For that, you might, for example, define a loop that you're, for example, a for loop that goes through all this like K from 1 to, I don't know, 15. Based on what your data is and calculate which K is giving you the best predictions. But anyway, at some point, you're going to see your predictions, for example, are going to increase. For example, from 1 to 3 is going to be a little bit better. From 3 to 5 is going to be a little bit better. From 2 to 7 maybe a little bit better. But at some point, it's going to decrease, okay? When you're going when you increase the K number to a big number, for sure, it's going to increase, and I'm going to later discuss why it's happened. For example, you see for 1, we get 96, 7, 3 gives us 97. So it's a low, it's getting a little bit higher, 5, it's higher, 7 is exactly the same. For 9, it's going low. For 11, it's going low, lower. 13, lower. 15, lower. So we get from 96, we went up to 98.5, and we went all the way down to 95% now. You see, so there is a optimum point there. Like for example, in this particular example, I'm getting this value, right? But at some point, it's going to go low. If you cannot, for example, put here 101 and expect to get a good result, because it's going to calculate. It's going to look at all this 101 closest. I don't know, closest neighbors and see if it can calculate good prediction or not. So you can see it becomes awful now, 93% accuracy. So let me see. So what if it's a question for you. what if I call it, oh, sorry, that's wrong. Okay, this is what I wanted to do. Here I'm calling it training set and train set. So why, the idea is why it's not good, you call your function again, okay, on the training set. So what I'm doing here, I'm training it with training set, and then I'm evaluating with training set, and I want to look at the one closest neighbors. Okay, this is not, this was that one. But what do you think I'm going to see for this?
Very good accuracy.
So you can tell me exact, I mean, you should be able to tell me exact number.
1.
Exactly.
Yeah, because the training is fit to the training set.
Yes, exactly, because I'm training it with this set, then I'm validating with this set, then I'm looking at that and only the first closest one. So of course it's going to be exact overlap. So the prediction would be 1 here. Of course, this is not what I can do. Okay, this is not a valid thing to do. Even this is not a valid thing. This is pretty like dumb things to do. You don't train, then you go back your training set to check it with that. So forget this. So you don't do this. Okay, you don't train with training set, then validate it with the training set. That's why we separated completely the test set that your classifiers haven't seen before, those values. That's why basically we are reshuffling earlier to make sure there is enough randomness there. There is no ordering or for any reason. So any questions about this so far? No? Yes? No? Okay. If no, let's go back to talk about. So you see, okay, if I go back here, no. Let me go here. Talk about this. So you remember this table, chronic kidney disease that we saw earlier, okay? So I'm going to look at this table again. So I scatter plot this based on hemoglobin and glucose, the one that we saw, it gives us a good predictions, okay? Good classifier, good predictions, we can do this. So I did this, I scatter plot this, okay? Then I wanna now know for this particular red dot, which is another, let's say a new sample that I get. Now I wanna classify this red one, okay? I want to put it in class 1 or class 0, or basically chronic disease or chronic kidney disease. So this is the one. So for this one, that's what we did, right? We calculate the closest one. So now I want to do closest point to this to see which class this point should be assigned to. So if I draw the closest point to this yellow one, I'm going to see this. I'm pretty sure the function is correct, okay? This is correctly written. So why this is the closest point to this red one, not this one? Or not this one, this one.
Because of the x is, the scale is smaller.
Yeah, exactly. It's like, as you pointed correctly, the axis X is increasing very gradually, while axis Y is like each step is 100. In axis X is like +2. So this is actually the closest one. But if I want to see, so this more precisely. So what I want to do is, what should I do if I want to have a same scale here? You see, these are the different scale, okay? These are increasing by 2, this is increasing by 100. So I want to have it same, basically, a scale here. What should I do?
You standardize the data.
You convert them to the standard units, right?
Yeah.
So I convert that to standard unit. I draw this again. So now you see this is the one closest, because now they are both in a standard unit. So now I can compare their distance between. So now you see this is the closest one. Basically, this is the same point here, okay? It's not that now this is the one. This is the same point, but now the scale is changed. This is in a standard unit. So this one is a standard unit. Now I see the correct one. So you see this is the closest neighbor to this. So in this particular example, I'm going to classify this as cancerous, right? I'm going to put this in a class 1. So what if I start moving the point to different place? So you can see for each step, what I'm doing, I'm calculating the closest neighbors. So here's that particular point is the closest neighbor. So in this jump, the closest neighbor is this, but still it's a yellow one, so it's a class 1. So I keep moving it. So it's the same class, same class. So at this point, it changed to the class. The class, basically, this yellow dot here, this blue dot is the closest one to this. So I'm going to now classify this particular point, okay, as class 0 or as not non-chronic kidney disease. So there is, you can see there is this particular point, like between this point and this point, my classification is changed. It's not a big step, small, slight difference, okay? So in this point, yeah, at this point, at this location, it's a class 1. At this location, it's class 0. So you can see there is a clear distinctions between where this point is standing and which class I'm going to assign this. So there is this line or this border between these values, right? You can, I mean, it's not drawn there, but you can imagine. After passing that particular imaginary line here, it gets closer to this, so the classification would change. So that's what I'm going to talk about. So that is basically decision boundaries. In what it is like the boundaries that my classification is going to switch. If it's here, it's going to be class 1. After passing this boundary, it's going to be class 0. So it's basically a change in input attributes might change the predictions. Of course, that's the case. Input that are very close but result in different predicted labels are on either side of decision boundaries. So if we consider that if there's 2 points, one is slightly above the decision boundary, one is pretty close to this one, but slightly below the decision boundary. They are pretty close, but they are going to result in 2 different classifications. So that is basically my decision boundaries. So to visualize that, we can plot predictions of regular set of inputs. Let me show you on that. Oh, I should have run this because it's going to take a few minutes to run. Okay. Let me see. Okay, while we're waiting for this running, any questions so far? All good?
Yes.
No doubt, no questions about what you're doing with k-nearest neighbors, decision boundaries, classification.
I have a question.
Yes,
Instead of, in the voting part, instead of, well, I think maybe be a solution, but instead of doing a fair votation, we can give a bigger value or bigger weight to the first 3 and give the others lower values. Maybe
so
will be a solution.
you're talking about this, right? For example, here, right?
Yes, that part.
So you're saying basically maybe the clump thickness is not that important comparing to, for example, uniformity of cell shapes, right? That's what you're saying. For example, why I want to give this more weight comparing to this, because this is more important in defining the cancerous cell.
Well, it may be, but I referred to the class part for the first 3K. Maybe we can give a bigger value for voting.
Okay. So you mean, for example, in order to do the predictions, you say, okay, I want to evaluate this, but then you say, okay, for the first 3, I'm giving the bigger weight than what I consider the first 7 neighbors, right?
Yes, for example. If we have a K7, we can give the first value a bigger weight and the 3 below a less weight, and the last one less weight for the voting.
I read it. It's a very interesting question. I honestly never thought about it. It's like, can we give weight?
Okay.
Let me think a little bit.
Well, I could evaluate later.
You can do that. I assume you. I don't really know if you're gonna get a better result or not. But yes, I'm pretty sure if you do that, then it's not going to be K-nearest neighbor anymore. It's going to be something. I haven't saw that before. And to be honest, I don't want to give a dumb answer. It's like I haven't thought about it. I haven't saw someone doing it, honestly. But it is pretty interesting to experiment around and see if you can, for example, improve the accuracy here. We say, okay, for example, for the first one, I want to say this is 99% important, the second one 95%, the third one 93% importance. Then I'm going to average them and decide my classification and see if you can increase this accuracy somehow or not.
Yes.
Might be, but
depending of the instance or something like that.
I'm not so sure. It might exist. I mean, they're in the research community, they're crazy. They do all sorts of experiments. It might exist, but I'm not aware of it, honestly. But I'll look for it. If I find something, I'll discuss with you or with the class for the next week. So this is
okay.
Still
thank
running.
you.
No problem. It's still running. I'm seeing it's busy here. So before this, let me talk about this one. I thought you want to say, I misunderstood your question. I thought you want to say, I'm going to give more value for, where is this schedule plot I did? Where is that? This one. I thought you want to say, for example, by weighting, I thought, for example, you say, another thing you can look at the weighting is like you say, this clump thickness look like so varied for me. It's like so random. Okay, I don't see any pattern here. But there are, I see certain pattern for these other parameters. So you might say, okay, I want to calculate the distance, but I don't want this to have a big effect on my distance, okay? Then you might say, okay, I'm gonna discard this because, or even that doesn't make sense because if there is no much variance here, then it's not going to affect your distance much. I'm just thinking out loud. So this is going to affect your distance much more than this because these are more uniform than this. So anyway, this is over. Let's look at it. So talking about the decision boundaries, the calculation is over. So this is what I'm doing here. This is a K value. Okay, this is the first one is it's the same one for chronic kidney disease for this definition that we saw on a standard unit, hemoglobin and glucose. So here I'm showing you the K1. That's basically one nearest neighbor or nearest neighbor algorithm, right? Where it's K is 1. So basically all the points that falls in this blue part of the histogram, I'm going to classify that as blue. All this one, I'm going to classify that as yellow, no matter where it's sitting. If my new point is falling here, that's going to be are classified as class 1 or chronic kidney disease. If here, it's going to be non-kidney disease. If I consider K1. If I increase my K to 3, you see I'm getting the different decision boundaries. And that is why, because now, for example, for this particular point very near to this one yellow one, I'm not going to just look at one nearest neighbor. I'm going to look at the 3 nearest neighbor. So this is one nearest neighbor. The other 2 closest neighbor to this point here is going to be these 2, for example. So then I'm going to average this voting. The voting goes to blue, right? That's why my decision boundaries change by increasing the K. That's why at some point I mentioned, at some point your K is going to get a good result, better, or maybe it's improved, but at some point it's going to go low. For example, in this particular example, this particular table, the K1 is going to give you the most accurate results. You can see it's exactly differentiated. There is a clear line between all the yellows and all the blues. If I go for K3, now this particular one and all the things that I'm going to be here, I'm going to consider them as non-cancerous. Even this particular one is going to be non-cancerous, which is absolutely wrong. So if I increase my K to 5, you see the border is changed. Now there are more points here. For example, these are having more blue line close to them than yellow one. If I go to 7, I get like this. So is it clear what I'm doing here? Is it? So you can see the changing your K value, how it's going to affect your decision boundaries, and basically how it's going to affect your results from all the way from 1 to increasing to 3, 5, 7. So as I mentioned again, for example, you see this particular one is pretty close to this comparing to the yellow one. But if you consider 7 closest neighbor to here, mostly they are going to be blue comparing to yellow. That's why they are going to be considered as yellow or class 0. If I look at another table, which is this was more diverse. These were these 2 values that VISA is not giving us a good estimation. So you can see in K1, these are my classification point. All these point that falls in the blue one, I'm going to classify them as blue. Those yellow one, yellow. So you can see it's not that smooth. Even those parts here, it's going to be yellow. Slightly the other side is going to be blue. It's going to be yellow. If I increase my K, now those small point has gone. Increase. So you can see how changing basically K changes your decision boundaries. Any question so far?
And for example, in that table, which is the best K?
In this particular example, we already said these 2 are not good how to say parameters to look at when you're trying to do your K. You remember we said you're looking at certain attributes of in your data, and based on that you want to do the classification. Here they are not good, but even for example you say, okay, this is what I have. Okay, I'm going to do something about this. This is what I have. So considering this, it's anyway you're going to get an awful prediction no matter what. But I would say maybe you go a bigger K, and just to make sure you're classifying the yellow one better comparing to I'll say non-kidney disease. But you cannot get a good result no matter what you do with the K. You always get a very bad estimation here. Maybe the one, I don't know. You can play around with it and see. Even in the case like this, in worst case, that everything is overlapped. There are blue here, blue there, blue there, blue there. Everywhere is blue. Yellow is everywhere literally. Of course, there are more blue here. You say maybe if you are here close to this one, the chance of you having disease is lower, but it doesn't still says 0, right? So it might be like, for example, by accuracy 90 or 85%, you say, if you're here, most probably you're fine. If you're here, 93%, 95%, you are going to have a problem. Any questions, other questions so far? No? It's, if it's not clear, please ask question because we are terminating with this. So to recap, whatever we talked is, oh, okay. The k nearest neighbor classifiers take a vote of the k closest points. How do you choose k? Use your test set and see what k gives you the best estimation. And talking about the decision boundary, it shows where the classifiers change its prediction, okay, based on basically the k. It changing k, it changes your decision boundary, it changes your classification. So you see, whatever we talk is basically k nearest neighbor classifiers. It's used in machine learnings. It's not the only one, not the only classifier. There are other classifiers. You know, for example, neural network, I don't know, decision trees, regression. Regression also can be seen as a classification for numerical value. This is more for categorical value because we are putting in this particular example, we are putting them in two categories: cancerous, non-cancerous, kidney disease, non-kidney disease. It's not necessarily should be just two categories. You might have different categories, but that's for categorical data, k nearest neighbors. Regression can be used for numerical data. We already saw that. And these are the example of how to say supervised learning. You can have, for machine learning, you can have supervised, unsupervised learning. Supervised learnings are those that you have a table that are properly labeled, and you train with this labeled data. So that's why we call them supervised, because you have a data that is perfectly labeled. For unsupervised learning, basically you give the data to the machine, and machines try to. It's not a labeled data, so the machine itself tries to. The algorithm itself tries to find the relationship between this data to find some sort of association between different parameters. So in this one, but it's a supervised learning because the data, what we are talking about, is already labeled, like cancerous, non-cancerous. So yeah, that's recapping today's class. Any questions so far? No? So if no, there are certain things I want to talk about. I'll try to go quickly. Maybe today going to be a little longer than that. So we're going to talk about decision under uncertainty to make sure your statistic is good. I mean, you're basically it's measure to see what you learn. So I give you 1-2 minutes to please read these questions, and I'm going to ask the answer. I mean, read it and try to answer. Let me put some. Right. What's happening? Let me see. Close this. Take it here. Close this. This one. So please read this. Oh God. Okay. Oh, where is this? Okay. So can you please read the questions? So after you read, please answer this question. So this is a study done in 1978. It's not a very randomized experiment that, but it's valid. It's been repeated again at some point. So I want to see what you think. So I got 8 votes so far. I appreciate if everyone votes. $11 votes so far. I'm not showing you so it doesn't affect your judgment. So half class voted, it's going up 14, 60%. So okay, I mean, just go for vote. Whatever you think, it doesn't matter really. What do you think is the correct answer? So 5 people are missing to vote. Almost. 2 more. I'm pushing you so hard, maybe. Okay, just last person, please. Okay, maybe he or she's not even sitting there. So this is what I got. So 10 people think it's the chance is smaller than 95%. 9% think it's exactly 95%. I assume they are looking at this 5% false positive. And 3% think it's bigger than 95%. So, what do you think? Can anyone share his voting? I mean, talk about the result of his vote. It's either it's bigger, small, equal, smaller. It's just your reason of why you think that is the case. I mean, don't afraid of being wrong. It's totally fine. Anyone? Or should I name? Oscar Alejandro? Are you there?
Yes, but I don't know.
So you voted, right? So just tell me you voted what and what do you think that's the reason?
But there's no reason. I just thought that it was most likely to be less than 95%.
Yeah, so that's the thing. You're saying it's most likely to be less than 95%. Actually, so why you think that?
That's the problem. I don't really know. I don't know.
Okay, so most probably you say, okay, there are 5% here is a false positive rate, so it cannot be bigger than 95% because there are 5% is a false positive. Then you may wonder, then what is about this 1/1000, like 0.1% chance? Maybe that's also playing some role. That's why I vote less than 95%. I summarize your basically thinking, I guess.
Yeah, but I was also thinking selecting equals to 5, not 95.
Okay, so you were between these two.
Yeah.
So anyone else? Eduardo Alonso, are you there? Anyone want to share? Cesar Augusto? I have doubt in you are sitting there. Come on, that's why I want you to see your camera. David Garcia, you want to say something?
I think I answered incorrectly,
So what
but
do you think is the correct
but
answer?
I didn't actually understand the part of the prevalence is 1/1000. I didn't understand like the translation.
Oh, sorry, it's like it
So
means it means
so I couldn't actually make a real decision.
sorry, I should have explained it. Sorry.
No problem.
It means basically the chance of one person getting that disease is 1/1000.
Oh, okay.
That's what it means. It means like 1/1000 a person can get that disease.
Oh, okay. Okay, so the chance that the person has it is 0.01 or 0.01, right? 1%?
Yes, 0.01%.
0.01%.
So you think that's the chance? But the person is already tested positive.
Yeah.
So you don't go. I come to you, I take I don't know anything about your symptoms. I just come to you, I say, I take the test from you, and I know the test has 95% positive rate, but I see your test result and I see it's positive. But I know already also this fact that one in 1,000 people can have this like disease.
Okay.
So
I think it's less than 95%.
Less than, but can you tell how much less than 95%, like 94%?
Oh no. I think it's way less, but not sure.
Way less. Okay. So the correct answer, this is the just bigger one. The correct answer is smaller than 95%. And as David Garcia said, it's way smaller than 95%. It's not even closer to 95%. So we're going to talk about this conditional probability. I'm going to go through this super fast. I'm pretty sure you know it, just maybe you don't take care of it sometimes. So just make it a scenario much simpler. You have this scenario. Classes consist of second year and third year students. You have in the class, you have 60% second year, 40% third year. 50% of the second year have declared their major, 80% of third year have declared their major. Let's say this is like a TC21 things that they are doing. We are doing is you go 2 years, then you declare your major. So I pick one student at random from this class. Okay. What is more likely, second year or third year?
The second year.
Second year. And why the second year? Yeah.
Because there are more of them in the class.
Exactly. You say there are like 60%, my class included second year. So if I take one person randomly, there are 60% chance that the person would be second year because there are 60% of the class is second year. So let's twist the question now. So the same class, the same value. Now I pick one student at random, but I know that the student has declared a major already. Second year or third year.
I think it would be most likely a third year.
And why is that?
Well, I'm not pretty sure how to explain it, but I think it's like the probabilities of getting a student that has declared a major that belongs to the third year are like bigger because we have like 80% of them.
Okay, so yeah, it's the way you think is correct. I mean, you can just explain it correctly, but I mean, good in a nice way, but it is correct exactly as you think. You say, okay, there are 60% second year, 40% in third year, but in this 60%, there are only 50% of them, half of them are declared, but in this 40%, 80% of them. So let's look at this. So this is what we have, 100 people in the class. 60 of them are second year, 40 of them are third year. So in this second year students, half of them are basically 50% of them declared. There are 40%, 30%, sorry, 50% declared, 50% not declared. In third year, the declared are 80% and undeclared are basically 20%. So if I divide this on the class, I'm going to get this distribution, right? So now looking at this, it's make it much easier, okay? So I pick one student at random, that student has declared a major. So now, can you tell me this, second year or third year?
Third year.
Third year.
Third year, right? Because now you just totally, you can ignore this two part, right? You can just look at this. You say, these are my declared students. I know already the student is declared, so I'm going to look at this. So now here I have 32 students here, there are here 30 students. If I pick one random from these two groups, there is more chance to have a third year students. So this is basically that the one that I was showing you, telling you, conditional. So this is basically based on Bayes rule. What it tells is basically this, I'm pretty sure you have seen this before in your classes. The conditional probability that you have the probability of the second year, given that, it's read as given that the students is already declared. So basically what you say, I wanna, the probability of second year, I wanna calculate this probability of the second year while the students is declared. So you calculated the probability of, this is the equation to say, basically the probability of second year and declared, this is 30% divided by the probability of declared, which is 30 plus 32, right? In this particular example. So this is that the conditional probability or Bayes theorem, basically Bayes theorem. You have probability of A given that B is happening, right? That's what you most probably saw, probability of A given that something happens. So you can look at this like in this way, okay? You have the second year, you have the third year students here. This is 60%, 40%, and this is 50, 50%, 80, 20%. So for year 60, you have 30% here now, 30% here. For this 40%, you have 32 here, sorry, this is 30 students, 32, and 80 students. So we call this prior probability, the one that you already have. This is the likelihood, or basically the second conditions. So the Bayes rule to calculate the posterior probability, or basically probability of A given that B is happening, or probability of third year given that the student is declared. So for this, you can calculate it this way. The probability of third year and declared divided by probability of declared. If you calculated this, based on this, you can just look at this part, right? This is third year and declared, third year and declared. So this is the probability. And probability of declared is basically this is declared, this is declared. So you're going to add these two. 6 multiple 5, 4 multiple 8. So looking at this in this three-way, it makes it much easier to understand. I'm pretty sure you know this. Just to remind you again, just to remind you to take care of it. So the purpose of Bayes rule or theorem is you need to update your prediction based on the new information that you receive. Okay, this is very, very, very important. Okay. In multi-stage experiment, you find the chance of an event at an earlier stage given the result of the later stage. So basically all the things that you find out during your study, that's going to affect your decision. So if you try this again now, what can you tell me about the basically percentage? I just, because we're running out of time, I don't wait for your answer. It's now given that what I talked already, so you can now see this question much more clear. So I'm telling you, I have this. This is my basically chance. I'm giving, what is the chance of the person is sick? Okay, given that this is the possibilities. So you can calculate that this way. This is the disease, the probability of one person have disease, this is no disease. So I tested positive, negative, positive, negative. This is basically for that 95%, 5% false positive. So if you do this, you put that in the equation, you're going to get just 2%. So it might sound pretty shocking, like I did a test, okay, the accuracy of test is 95%, but the chance of me being sick is just 2%. Is it rational? What do you think? Or there is something wrong?
I believe it's correct.
So David Garcia believes it's correct. Anyone else?
Why is the probability of being, I mean, the 1 and the 0 in the disease?
This one?
Yes. Why? I mean, shouldn't the test have the same probability for a person in regardless of if the person is sick or not?
No. There was this condition. Maybe, sorry, I skip it. Maybe I skip it fast. This one.
Ah, okay.
Assume that if the person has a disease, the test will always be positive. I mean, you may consider it, you may calculate it without this, okay? It was just to make it simplify this part. But that's exactly valid. If you say, okay, if I'm still disease, the test should give me 95%, right? You can calculate it that way. It doesn't change the fact. This is going to be very, very small number.
Okay.
But this is for that condition that I put earlier. But this is actually, as David Garcia said, is absolutely correct. There is nothing wrong with the calculation. But it might be a little bit, sounds weird for you that I did the test, I find they telling me that I'm sick, but is there really just 2% chance? But remember, here I'm talking about going to a person, taking the test randomly. What would be the case, okay, if you see some symptom, you go to the doctor, okay, then the doctor gives you the test, then you end up positive. This calculation now would change slightly because there is another knowledge now you have. You know there is something wrong inside you. You feel something. That's why you went to the doctor. So this would be higher than this. So this is what basically the idea was, talking about subjective probabilities. So you can look at the probabilities in two ways, okay? The outcome of the probability. The first one is the frequency with which it will occur in a repeated trials. This is what we saw in most of the class. You roll a die 1,000 times, you expect to see a 6 happening like 1/6, right? That's basically based on the repeated trials, you expect to see some outcome. But another way is the subjective degree of belief that it will or has occurred. So basically, you may wonder how the probability can be subjective, okay? But actually, it can be subjective a little bit. I'm going to talk about it quickly. So that's the question. When the subject of your prediction was not selected randomly from the population, in that example, I'm telling you, you go get a random person from the street, do the test, the chance is just 2% that the person is sick, or even those facts. But if you go to a clinic that people are coming because they have some certain problems, then those calculations would change. That is not, now your subjects are not randomly selected. They are people with some symptoms. So in order to quantify a belief that is relevant to what I'm trying to say, so let's look at this, the other one, the same example. Now we say the chances of the person is sick, okay, is 5%. Now you know 20 people out of 1,000 people, they're going to have that disease. So now you calculate this, you're going to end up with totally different percentage, because this is already changed. This prior belief is already changed. So the result would change drastically. So talking about this, I'm going to talk about this very quickly. There was this experiment. It's basically, there was this experiment in 2001. Okay, there was this operation, they were this experiment opera that they were trying to basically speed up the particles, atomic particles, and they hit them to each other. Basically, that's what they are trying to study for finding, for example, dark matter, origin of the universe. So they speed up the atomic particles, they hit them with each other, then study the effect or the particles that generate from this heating to atom together. So at some point in 2001, there was this experiment. They were doing this, and they find out the outcome of some experiment was they find some particles that are traveling faster than the light, faster than the speed of the light. So if you're familiar a little bit even with physics, you know that's impossible based on the rules of physics. Nothing goes faster than the speed of light. That's a base, okay? You know that by fact. So if you're physicians, you know this by fact. Seeing that result that your machine is giving you, that there are some particles going faster than the speed of light, simply you say the machine is broken, right? That's the conclusion you get. There is something wrong with this experiment. The machine is not adjusted properly. Something is wrong with the machine. That's why I get this weird result. But what happened in that particular example, the message gets circulated, arrived to some reporters, and the reporters started putting that in the weblog. It get noticed by the big news media. Then they started putting that in the news that, that the physics is broken, the fundamental rules of physics is broken. There are some particles that can go faster than the speed of light. It becomes big news. Why it happens? Because for physicians, it's a fact, okay? Nothing goes faster than light. For reporters, it's not, okay? So it's possible. So that's how it affected their judgment, and they see different outcome of that experiment. So I'm telling all this to basically tell you about that, basically your priors matter, how you think about it, what is your experience on certain topic, it's going to affect your judgment about the results that you get. But to recap everything, Bayes' rule, let us calculate conditional probabilities. Just remember that. You know the rules, just remember how you can apply it. You can draw the tree of events to help you to make the calculation. It's just make it visual. When you visualize it, you see it much clearer. You can see that. And also remember the count for your priors. But you know already those things are going to affect your judgment. So we finish. Sorry, it took longer today. So we finished with data science course. Yeah, Alan, you really deserve that. It's great. Sorry it took longer today. I just wanted to finish with everything today, so nothing left for next week. Just talking about the exam, doing the practice, invited speaker. If you have any doubt about anything that so far we discussed, you can ask. You can bring those issues next week to discuss. But anyway, this was basically fundamental course on the data science. You see, we touch a lot of things, very surface of it. Machine learning, very basic, just giving you the broad idea of it, classification. We talk about regression, I don't know, bootstrapping, a lot of other topics like that. If you're really interested there, you can continue with more statistics, studying that, going now deeper in machine learning. I don't know, studying how to big data analysis with the applications. I don't know what to say. That's it really with the class. Is there any questions about what we discussed?
Not for me.
Okay. I hope you really gained what you were looking for this. I basically, I told you the first day the course was designed by the Data 8 course from Berkeley, UC Berkeley. That was basically, the content was from the UC Berkeley, the slides was from UC Berkeley, but it was one of the toughest course I ever teach. I mean, it took me a lot of time to prepare everything, honestly. But I just wanted to follow their footsteps because I find it pretty interesting the way that they taught the course by tons of experiment, real data, table that you can modify. So I thought this make it much interesting, though it might have been a little bit heavy on the load of homeworks, lab projects. But I hope you really learned things that you were looking for this course. I have updated the scale. You can see it still. Okay, yeah. I have updated the. Let me stop the recording. No, it's fine. I have updated the Excel file. You have all the things is updated. Just what is missing is the last lab that I haven't graded, last homework I haven't graded, project 3 that I haven't graded yet. But everything else is updated. You have the solutions in your shared folder. So I'm going to be slightly more, to be honest, I'm going to be slightly more comfortable here for lab 9, homework 7, lab 9. I'm going to give you full grade, but please do it, okay? I don't want to tell you don't do it. Please do it, it's just going to help you, okay? The whole idea is learning, not, that's very not true. The grade is important, but the whole idea is, the main thing is learning here. But please do it, please submit the complete one, okay? Doing all the things. But you can consider you're going to get 100 for this, but for project, I'm going to grade it carefully, okay? So if there's no question, just for next week, please come because it's important. We're going to talk about the final exam, and you might have invited speaker talking about their experience in industry, what they do really. Thank you, guys. See you next week.
Thanks, Professor.
Thank you, teacher.
Thanks, teacher.
Thank you, guys. See you next week. Bye.